So the LeetCode problem we are going to solve now is called longest common subsequence. Now we can see that this one is a LeetCode medium problem and also one of the most liked problems on LeetCode. So I'm going to pay my utmost attention. Now let's understand the statement. We are given two strings called text1 and text2. Now we need to return the longest common subsequence. And if there is no common subsequence that exists, then we need to return 0. Now we are given the definition of a subsequence is a string, that is a new string that can be generated from the original string with some characters that can be deleted without changing the relative order of the characteristics. So without getting too much into the details of the definition, let's try to understand what we are being asked to solve. Basically, we are given two strings text1 and text2. Now we can notice that text1 currently has 5 characters A, B, C, D, E, and text 2 has currently 3 characters A, C and E. Now the thing is, if say for an example from text 1 we decide to eliminate this characters B and D, we can also create A, C and E, and this is going to be the exact same manner, or the sequence of relative order remains the same between both the strings. So we can say that for this given example, we actually have a longest common subsequence that we can make that follows the relative order, and that is of size 3. So we need to return 3 as part of the answer for in this case. Now let's try to understand it with one more example for this one. Now we can see that currently the characters we have is x, y, z, and the characters we have for this text 2 is y, a, b. So now we can only find one character that is common between both of them and that follows the relative order, and that is this y. Apart from that, we don't see anything common. So in this case, we can only create a longest common subsequence that only consists one character. So we need to return 1 as the answer. Now if we take a look at this example text1 and text2, we see that there are no characters that are same between both the text. So in this case we will have to return 0. But in the same example, say for some reason, if we are given the values like a, b, c and d, e, f over here, and then we are also given d, e over here, then we will need to return 2 as the answer, because the relative order of d and e remains the same even if this string had 3 additional characters. So we will have to solve this problem, and definitely this is going to yield to some very interesting results. Now let's understand the brute force approach to solve this problem. The logic is quite straightforward. Let's say that we are currently given two strings in this particular fashion. Then what we can do is we can go through every single possible combination of any particular string and try to match it with the other string. So what I'm suggesting is that for this text one, we start taking permutation of all the other substrings that we can make out of this one. And we know in terms of making permutations, we can actually make 2 to the power of n permutations for any given value. Why? Because at every single character we will have to make the decision that whether we need to include this character or not to include this character in order to generate the permutation. So this would eventually yield us the correct result, because what we'll do is we'll try to create all the different permutations and combination, compare it with this given another string, and we'll try to see that what is the longest common subsequence that we are able to make. But this is very inefficient approach, and also the time complexity goes in some sort of exponential form. So I'll not go into the depths of this one, and we'll try to do something smart in order to solve this problem. Now let me come to the optimal way to solve this problem, and for that we are going to use one of the most beautiful concepts in computer science, and that is dynamic programming. Now let's take a quick recap. Let's understand that why do we actually have to use dynamic programming in this problem. Well, the answer is actually quite straightforward, because let's say that we are currently given the two strings as a, b, c, d, e, and then once again a, c and e. Now notice that if we start comparing the two strings at any given moment, character by character, it would not be very much fruitful. Why? Because okay, let's say that we define that this a is common between both of the subsequence. Now we are at this character b, and we don't know that next character b is not present over here. So we don't know that whether b is going to be present somewhere down the road or not. So do you think that we should compare b with every other character that is currently present inside the t2 string? Well, we could do that, and we are going to do that, but In order to do that, we'll also have to remember that what was the relative order of sequence that we have been able to identify beforehand. And it could be possible that if we are dealing with multiple sequences, which subsequent to consider. So let me give you one example like this. Let's say that we are given currently strings like a b c d e, okay, and we are given the t2 string to be a b, then x y z, and then once again we are given the string to be, let's say, b c d e. So do you think that from this particular point forward, if we see, the longest common subsequence we can make is going to be 2? But the moment we start identifying these characters, we can, if we just drop this b, we can actually create the longest common subsequence of size 5. But we have to drop one b that was already part of one of our relative subsequence, which means the result that we are going to make later down the road is actually going to be dependent on the previously calculations that has been made, and also future calculations that we are yet to be make. And when we are at the last position, we should make the best judgment on which path to take. So that's why this is a good candidate for dynamic programming. Now the question is how we are going to use dynamic programming to solve this problem. And for that, what I'm suggesting is, number one, we have to check every single character for all the other characters, and same way for any particular character we will have to compare it with all the remaining characters. So there is no getting away from that in this problem. We will have to do n square work, or m multiplied by n work, where m is the length of text 1 and n is the length of text 2. Okay, so this has to run in big O of n square time complexity. But how we are going to do that? Number one thing I'm suggesting is that we actually create an m cross n grid, just like the one that I have shown over here. And for this particular grid, we'll need two things for our dynamic programming. We'll need a base case scenario. So base case is quite straightforward, that if any particular character is not matching with the other character, then we simply define it as 0. And notice that we actually have created an extra space at the beginning. So there is an extra row and extra column, which means this is not strictly an m cross n matrix. This is actually an m plus 1 multiplied by n plus 1 matrix. So we are adding one more extra line, and that is to consider our base case. Now at any given moment, what we are going to do is, if we identify that there exists a combination, there exists a value that is common. Let's say that over here the c and c is going to be common for this particular cell, which means what we can definitely say in this case is that this cell is going to be an addition to the previously calculated longest common subsequence. Now where is going to be that information for the longest common subsequence? To the diagonal value. Why it would be at the diagonal value? Well, let's take a simple example. Let's say that currently the values are a, b, c, and this value is a, b, and c. So notice that for this particular square, the logic is going to be quite straightforward. We are going to have a and a common at this place, then we are going to have b and b common at this place, and then we are going to have c and c common at this place, which means longest common subsequence is directly represented towards the diagonal value in the best case scenario. And this is the fact that we are going to exploit. So whenever we identify that at this particular location there was a common subsequence, then we had to add one value to the previously found longest common subsequence. But we haven't found any subsequence because this value is 0. So definitely the longest common subsequence at this 8th location is going to be 1. So we are going to mark it by 1. Same way, the longest common subsequence at this location is actually now 2, because we are comparing AB with AB, and that's why this is going to be an addition to the diagonal. So we are going to mark value 2, and same way this is going to be value 3, one more addition. So same logic we are going to apply over here, that whenever we identify any particular common characters, we will check the diagonal value. That is number one thing. Next thing is that let's say we identify any particular character that does not have any common values, so both characters are different than each other. Then it becomes the question that what is the longest common subsequence we have found so far. And there can be two possibilities. Why? Because let's say that I'm currently at this bth position. So on one side I'm checking against AB, but for AB I have checked with A, I have checked with AC, and I have checked with ACE, because I'm trying to fill up this row. same way for any particular cth character, I'm also comparing it against a, against ab, against abc and whatnot. So the answer for the longest common subsequence where the characters do not match is actually going to reside on the adjacent cells for any particular cell. So let's say I'm trying to consider the values for this cell. Now we know that b and c don't match, so in this case we'll have to check that what is the longest common subsequence we found either way, because we are not only comparing text 1 with text 1 or text 2 with text 2, we are comparing them with each other. So we'll have to take the maximum value amongst the adjacent cells, and this is going to yield us the correct result. So now let's recap our rules. Number one, if we find equal characters, so let's say that if an I and j value are equal, then we are going to do the plus 1 operation compared to its diagonal value. So diagonal value is going to be I minus 1 and j minus 1, this cell. Okay, and if that is not the case, if we find that I and j character do not match, then we will have to find the maximum value from its adjacent values or subsequent neighbors. So now let's try to do the solution right now. Okay, let's start filling up this particular whole matrix. Now very first value we find a and a, there is a match. If there is a match, we are going to compare it with its diagonal value and add 1. So diagonal value is 0, so we are going to add value number 1 over here. Now next thing is that we will also have to check, let's go row by row. So now we are checking this a with this value b. A and b do not match. So if they do not match, we'll have to, for this cell we'll have to check its neighbors. So we check this neighbor and this neighbor, and whichever is the maximum value we add this one. So what we are saying is that up until this point inside our input, we have calculated a b with a. So in this text 1 and text 2, we can see that the longest common subsequence we find was of size 1, and this is what we are defining it over here. Next we are comparing a with c. Once again, a with c, once again there is no commonality, so we'll add value 1. A with d, once again no commonality, so we'll add the maximum value 1. And a with e, once again the maximum value is going to be 1. Now let's repeat the same operation once again, but now this time we are going to be doing it for value c. Now c and a do not match, so we'll try to find the maximum amongst these two value, and once again the maximum value amongst these two is still going to be 1, so let's just mark it as 1. Same way this is going to be 1 as well. Now we are at this position of c matches c, so we'll have to do an increment with the diagonal value, and we are going to be adding plus 1 over here, so we can mark this as 2. Now for this d with c, we'll have to compare the maximum amongst these two, and the maximum value is 2, so we'll mark the value as 2 as the answer, and same way 2 as the answer over here. Now we are comparing e with this a, so once again the maximum amongst these two values is going to be 1, and notice we found 2 over here, but why we are marking 1? Because notice what we are calculating or comparing so far. We are comparing a with value a c e. So in this case the longest common subsequence is going to be of size 1, and that's why we are marking 1 over here. Same way this is going to be 1 because we are comparing the maximum amongst these two. Same way with c, we are now the value is going to be 2 because this value was 2. And why it was 2? Because notice we are comparing the values a b c versus value a c e, and amongst this comparison we can see that there exists the longest common subsequence of size 2, that is, which is represented over here. This is the beauty of dynamic programming solution. Now for this d comparing with this e, once again we'll choose the maximum, so answer should be 2. And now we have e common for this last cell, so we'll have to do plus 1 with the diagonal, so 2 plus 1 is going to be 3, so we'll mark it as 3. In the end we simply need to return whatever we find in the very last cell as part of the answer, and that is going to be 3 in this case, so we can return this with confidence. See how beautiful this solution looks. All we need to do is just fill up this matrix and things work out beautifully for us. Now if we have to calculate the time and space complexity for this one, time complexity is going to be big O of n square or m multiplied by n, and space complexity is also going to be big O of m plus 1 multiplied by n plus 1, so we can say m cross n for simplicity, but anyways this is a beautiful time and space complexity and very awesome approach. Now let's see the coding solution for this problem. Basically, we are going to define two characters m and n to define the length of both of the given strings text1 and text2. Then we are going to initialize our new array dp array. Now notice that we are defining it as an length of m plus 1 and n plus 1 to take care of the zero case scenario that is going to be our base case for our dynamic programming table. Now for this matrix, we are going to fill in all the details. So we are going to use two for loops to iterate over every single row and every single column. Notice that we are starting the values from 1 and 1 because for ith value of 0 and jth value of 0, we already defined the values as 0. Now first thing we are checking is that at any given moment we identify that the character at I minus 1 and character at j minus 1 location are equal to each other. Then for the current ith and jth value we are going to add 1 to the existing diagonal value, that is I minus 1 and j minus 1 value inside the dp array. If that is not the case, then we are simply going to pick whichever is the maximum value for any particular ith and jth element from its adjacent neighbors. So whether the top value or the left value of any given cell. And in the end, we should have completed all the values for the longest common subsequence, and the very last element inside our dp array is going to represent that. So we are simply going to represent that value that should give us our correct longest common subsequence. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 90% of all the other solutions. That is excellent in terms of time complexity. Now for the memory, we can improve on some aspects, but we are using like an m cross n grid, and that is also a fine enough solution. But overall, this is a beautiful solution, and once again, it is available on our GitHub repository, so feel free to go ahead and check it out from there. Thank you.